All right, let's talk about integrating some trigonometric functions. This is 7.3. And so we're going to talk a lot about integrating sines and cosines and tangents and secants in this section. And there are a bunch of formulas that your textbook mentions in this section that could come in handy for you. I'm a little bit reluctant to to give you these formulas because when I was taking calculus, we didn't use these. We just kind of derived them all on our own as we worked through the problems. And I'll actually show you an example of how you would do number one without using this formula. So I'll give you an example of that. However, after going through the section and kind of looking at some homework problems and stuff, I realized, it would be useful for you to have these so that you're not spending an hour on one problem, right? So these things might come in handy. I wouldn't necessarily advise you to commit them to memory so much, but they're useful things to kind of have on hand to help you through some of the homework problems. And I've numbered them because sometimes in the homework it might say, use formula 12 to evaluate this integral. And so you'll want to know what formula 12 is. I mean, I'm not sure it'll be that way on this particular homework assignment, but I've just noticed that in the past. So anyway, so I numbered the formulas so that they are like the form, so that they correspond to the formulas the way that your textbook has numbered them. Okay. But let's just look at some examples. So this first one says, find the volume of the solid obtained when the region under y equals sine squared x over 0 pi is revolved about the x-axis. And I wrote a note to myself, do this without the reduction formula. So I'm going to do it without using this formula right here, which you'll see why we would need to. But so let's do this. Y equals sine squared 0 to pi. Okay, so first of all, obviously you have to get a graph for this thing. So I don't know exactly what sine squared looks like, but I know that it's going to take anything that was negative and make it positive. So instead of going sine would kind of do this type of thing, right? And cross through, but sine squared is going to have to just touch and then come back up, which means your inflection points are going to happen kind of a little bit more quickly, right? So it's going to look something like that, I suppose. But we're only interested in the stuff that's taking place between 0 and pi, so that would be this stuff right here. And we want to know what's the volume when you revolve that region around the x-axis. Okay. So that's a disk thing, pretty straightforward, right? So if you imagine revolving it around, you take some kind of vertical slice, you're going to get a disk, and that disk is going to have radius, whatever the height of the function is. That would be the function value, sine squared x. So the volume is going to be pi times radius squared. Add them all up between 0 and pi. So it's going to be pi times radius squared. Okay, so there's the volume, disk method. So then you get a sine to the fourth, right? You might be able to hear my dog snoring. That's my dog, if you can believe it. Anyway, so sine to the fourth, that one is Vader. Vader the black pug. Anyway, so sine to the fourth. So now, if you wanted to use this formula, now would be the time to do it. So you could say, oh, well, it's just all of this stuff. But I wanted to give you at least one example to show you, how we arrive at that formula. So what we do is actually we think of sine to the fourth. The way that I originally wrote it down is sine squared squared, and then sine squared. You have an identity for that you should have learned in trig. You know that sine squared should be 1 minus cosine. The sine squared x should be 1 minus cosine 2x over 2. Or in other words, 1/2 times 1 minus cosine 2x. So what I'm going to do is I'm gonna like think of it the top way. And I'm going to say this is pi times the integral from 0 to pi of 1/2 times 1 minus sine 2x squared. Or sorry, squared. Right? So I've got to square the whole quantity. Okay. Okay, and so then I can square the 1/2. It becomes 1/4, and then I can take it out. So it's going to be pi over 4 integral from 0 to pi of 1 minus sine 2x squared. I'm going to go ahead and just expand that, right? So 1 times 1, so I have a negative, so I'll have minus 2 sine 2x, and then negative sine 2x times sine 2x will be plus sine squared 2x dx. Okay, and then for the sine squared 2x, you can use this formula all over again, right? So you can say, so that's going to be pi over 4 times the integral from 0 to pi of 1 minus 2 sine 2x plus 1/2 times 1 minus sine, and you've got a double angle from 2x to 4x dx. And there you go, right? So now at this point I'm going to kind of cut to the chase because you've got the idea now. I mean, well, maybe I'll take it a step further. Because if I distribute the 1/2, I've got a positive 1/2 plus a 1. That's going to give me a 3/2 for my leading term. And then I'll have a minus 2 sine 2x. And then I'll have a minus 1/2 sine 4x dx. Okay. And then from there, you can see, you can kind of see how you're going to end up with like a 3/2 x. And then this thing, you could do some kind of like u substitution, right? And same thing here, you could do a u substitution. And anyway, if you squinted it just right, then you see why you end up with something that looks kind of this way, right? So anyway, so from now on, you're welcome to use this formula so that you don't have to like do this every single time. But I just wanted to show you kind of at least once the derivation, and also to just kind of, I guess, pat myself on the back, because like I said, when I was a student, my instructor, I guess, didn't give me this formula. He just wanted us to do it this way every single time. But anyway, so I'll leave the rest up to you. I mean, the rest is history. Okay. So that's it for number 1. You could go through a same thing through a similar line of reasoning if you had like a cosine to the 4th, or if, or whatever, like a sine cubed, or well, actually with the odd ones, what you do is you peel one of them off. So you'd have like a sine squared times sine. And then the sine squared, you could use the Pythagorean identity, call it 1 minus cosine squared, and then do a u substitution, let u be cosine x, and then du is going to be sine x dx, right? So then the u substitution helps you. So actually the odd ones are nicer than the even ones. So when you've got odd exponents, that's not difficult at all. The even ones require you to do this like kind of recursive type of like thing with the power reducing identity. Which is kind of annoying, but anyway, but that's how you take care of those. And in general, you've got this. So let me say this about these formulas, right? So in general, you've got this formula, which you might notice involves like sines and cosines. And you might wonder, well, how is that when if I look at like one of these up here, this is all in terms of sine, right? This is all in terms of cosine. So why do I have these things? And basically, it has to do with just trig identities. I mean, like, you can always rewrite, especially when you have even exponents, you can use like Pythagorean identities. You can use the power reducing identities that we just looked at in this example to rewrite them. So you can kind of rewrite them. It's just difficult to do in general, and so they leave it this way. But anyway, I think that's all I want to say about the use of these things. The real thing that I want to tackle now is like, what if you've got both, right? Like, what if you've got a sine to some power times a cosine to some power? How do you deal with those situations? And your book actually does a fantastic job of describing what to do in this scenario. So they've got a table on page 425 of your textbook, and this is what it looks like. So let me pull it up for you. Okay, it's table 7.3.1. Again, this is on page 425 of your textbook. And this is almost worth copying down, I think. But it tells you exactly what to do. So, okay, so here's what you do, right? If your cosine exponent is an odd number, okay, whether the sine exponent is even or odd, it doesn't matter, right? If the cosine exponent is odd, then what you're going to do is you're going to split off a factor of cosine x, okay? Then you'll be left with like since cosine was odd, when you factor one of them off, you'll be left with an even exponent now. And so you can use this Pythagorean identity to rewrite it. And then what you'll have is sine to some power times 1 minus sine to some power. And so you can let u be sine x. And then du is going to be cosine x. And remember, that extra cosine is what you peeled off to begin with, right? So that's what you do when n is odd. Whether m is even or odd, it doesn't matter. As long as n is odd, this is what you would do. If m is odd, okay, so if your sine exponent is odd, then you do the same thing but with sine, right? So instead of splitting off a factor of cosine, you split off a factor of sine, use Pythagorean identity, and then substitute u equals cosine x. And a very similar thing is going to happen, right? The only question is, so that's what you do as long as m or n is odd, right? Whichever one is odd, you take that one, you split it off. If they're both odd, then just choose one. It doesn't matter which one, okay? Just choose one, split off a factor of the one that you chose, use the appropriate identity, and then make the appropriate substitution, right? So pretty straightforward. Now, what if both of your exponents are even? So if m and n are both even, what do you do? Well, with that, you have to use these power-reducing identities like what I showed you a second ago. So you just have to use these identities to reduce the powers on these things. So let me take you through a few examples of this. So let's evaluate some stuff. Let's do the integral of cosine cubed x sine to the 5th x dx. Okay, so this is a scenario where both of the exponents are odd, and so you just choose one of them, whichever one you like best, to kind of peel apart. I don't know where my pens all went. I usually have a set of colorful pens. I wonder if my kids got into the drawer here and took all of my colors. Oh no, here they are. I just placed them somewhere. Okay, so let's do this. Okay, so you just choose one. I'll choose, let me see what my next example is. So in my next example, I've got a cosine to the 5th. So in this one, I'm going to pick on sine. I'm going to pick on this sine. All right? So I'm going to call this cosine cubed x sine to the 4th x sine x dx. Okay, and all right. So sine to the 4th is really sine squared squared. And sine squared can be written as 1 minus cosine squared. Okay, so now notice that everything is in terms of cosines here and sine there. So I'm set up to let u be cosine x, because if I let u be cosine x, then du is going to be sine x dx. Now you may wonder, well, why didn't I just do that from the beginning? Well, because from the beginning, if I let u be cosine x, du is going to be sine x dx. That's great and all. That takes care of one of the sines, but I have 4 sines left over. So what do I do with those? Well, basically what I do with those is turn them into cosines, right? So that's the idea there. Anyway, so I can square that now and get cosine cubed x times 1 minus 2 cosine squared x plus cosine to the 4th x. And then I can distribute in the cosine cubed. So I've got cosine cubed x minus 2 cosine to the 5th x plus cosine to the 7th x sine x dx. And then let u be cosine x, right? And then du is going to be sine x dx. And making the replacements, we get u cubed minus 2u to the 5th plus u to the 7th du. The rest is history. So I'm not going to finish it. Okay. What I do want to show you maybe is that, you know, if we had made a different choice, this would have gone a little bit easier for us. I wanted to pick on the sine because the next one I'm going to do cosine, but let me just show you. If we had chosen cosine to peel off a cosine, then we would have had cosine squared x sine to the 5th x and then a cosine x dx. And now this cosine squared I can rewrite as 1 minus sine squared, right? So I would get 1 minus sine squared and then I would have sine to the 5th minus sine to the 7th and then let u be sine x. Oh, here I made a mistake, didn't I? U was cosine x, that means du would be negative sine x dx. Okay, so then I would have to have a negative sign out here. My apologies. Okay, but on this one, I really will get du equals cosine x dx. And now this just becomes u to the 5th minus u to the 7th du. So quite a bit easier, and you get there a lot quicker. Okay. You may, of course, wonder, well, how in the world are you going to end up with the same thing? And the answer is you're not going to end up with something that looks the same, but you will end up with something that's equivalent mathematically. And if you did a bunch of trig identities, then you could eventually prove that what you end up with is the same. Anyway, but this one's better. It's quicker. It's easier. It's nicer, more compact. Okay, so that one, you know, you can choose which one to pick on. Let's look at another one. So let's do sine to the 4th x cosine to the 5th x dx. This one's more straightforward in the sense that there's no ambiguity, right? You do the one that has the odd power. That's the one that you peel off. Okay? So we would get sine to the 4th cosine to the 4th cosine. The cosine to the 4th we rewrite as cosine squared squared, and cosine squared is 1 minus sine squared. So this is going to be sine to the 4th x times 1 minus sine squared x squared times cosine x dx. Okay, and let me show you this, right? So in the past, like on these past two problems, I waited to do the u substitution until I had done all the simplification. You don't have to wait. You could do the u substitution now. I mean, it's really clear. If you let u be sine x, then there's its derivative, right? And then this is going to be u to the fourth times 1 minus u squared squared. It's just a little bit easier because there are fewer symbols to carry around at that point. If you just do the u substitution now, right? So let u be sine x, then du is cosine x dx. And you've got u to the fourth times 1 minus u squared squared du. All right, so pretty straightforward from there, right? U to the fourth times 1 minus 2u squared plus u to the fourth du. And that's u to the fourth minus 2u to the sixth plus u to the eighth du. And I'm not even going to finish it. I mean, you know, u to the fifth over 5 minus 2u to the seventh over 7 plus u to the ninth over 9 plus c. Make the replacement, right? Back substitute, put in sine x for u, and you've got it. Right? So that's that. So let me give you the last case, right? So we've looked at one where they're both odd. We've looked at one now where only one of them is odd. If they're both even, those are the hard ones. If they're both even, that's when you've just got to do a bunch of like trig substitutions, right? So let's look at sine to the fourth x, cosine to the fourth x dx. Okay, what to do about this monstrosity? So for these ones, you're going to use an identity, but you're not going to use the Pythagorean identity. The identity you're going to use is the power reducing identity. The reason for that is because okay, so the reason for that is because if I call this like, let me give you an easier example, actually. Let's say that you just had, so we'll come back to this one here in a second. Let's say that you just had sine squared, cosine squared. Now, obviously, if I use the Pythagorean identity on both of them, they're just going to end up swapping places, right? And I'm still going to have sines and cosines. The idea is to get it all in terms of one function. So maybe I just rewrite sine as 1 minus cosine. Right? And then that would give me cosine squared x minus cosine to the fourth x dx. And at first glance, that seems really promising, right? Except when you realize that there's no u substitution that you can do now because you don't have because if you let u be cosine x, then du is going to be negative sine x dx, and you don't have a sine x sitting out here, right? And so that's the issue with doing the Pythagorean identities on this one. So you don't want to do a Pythagorean identity, you want to do a power reducing identity. So let's go back to the problem. So we're going to do a power reducing identity. So the power reducing identity, again, we're thinking of sine to the fourth as sine squared squared, and cosine to the fourth as cosine squared squared. And so sine squared squared is 1/2 times 1 minus sine, or 1 minus cosine 2x squared. Right, so there's the power reducing identity for sine. And for cosine, it would be 1/2 times 1 plus cosine 2x squared. Okay, that'll get us all the way from, right, I'm kind of doing like an intermediate step where I'm thinking of this as sine squared x squared times cosine squared x squared. And the sine squared x becomes this, the cosine squared x becomes that. Okay. Okay, but now for some arithmetic. 1/2 squared is 1/4. 1/2 squared is 1/4. 1/4 times 1/4 is 1/16. And I'm going to pull that out of the integral. Now I have 1 minus cosine 2x squared times 1 plus cosine 2x squared. Well, I can pull out the exponent and call that 1 minus cosine 2x times 1 plus cosine 2x squared, right? Because exponents, they don't distribute across addition and subtraction, but they do distribute across multiplication. So I can just pull that out. And what's nice about that is that this is a difference of squares now. This is just 1 minus cosine squared 2x. One minus cosine squared 2x squared, don't forget. And 1 minus cosine squared is what? It's sine squared, right? So this is 1/16 times sine squared 2x squared. Sine squared squared is sine to the 4th. You get 1/16 sine to the 4th 2x dx. And now you've taken this problem that had sines and cosines. You've whittled it down so that it just has sine, so that you just have one function, right? You just have one function here. And this thing, you know, you can use this identity on now, right? Maybe before you do, you've got to get rid of the 2x. You can do that with a u substitution, right? So you can say, let u be 2x, then du is going to be 2 dx. And so I can give myself a 2 dx here as long as I offset it with a 2 out there, which will make that a 32. So then I've got 132 times sine, times the integral of sine to the 4th of u du. And then that's going to be 1 over 32 times sine to the 4th is 3/8 u minus 1/4 sine of 2u plus 1/32 sine 4u plus c. Goodness gracious. And then you can back substitute. I mean, I'm not going to finish, but that's the idea there. You know, now that I'm thinking about it, what would have been wrong? What would have been wrong with this? Because you can split that integral, and we have formulas for cosine squared and cosine to the 4th, you know, the same way that we did for this one. Maybe, okay, this was for the easier problem, though. This was for sine squared, cosine squared. I bet for sine to the 4th, cosine to the 4th, it's it's going to be a lot more complicated. So this is just a more straightforward method. Anyway, so yeah. So that chart in your book is really nice. It's really, really good, concise advice for how to deal with this situation. Okay, so that's all I'm going to say about sines and cosines. Let's look at some secants and tangents. So just like with sines and cosines, there are a whole bunch of useful formulas that I don't expect you to memorize, but that could come in handy. And these are from your textbook, right? Some of these you should have memorized, right? You should know that the integral of tangent is natural log of secant, right? the integral of secant is natural log of secant plus tangent, right? By the way, derivative of tangent is secant squared, and derivative of secant is secant tangent. So it kind of makes sense, right? I mean, it's not exactly, it doesn't correspond exactly, but it's like derivative of tangent is secant squared. So the integral of tangent is natural log of secant. Derivative of secant is secant tangent. So the integral of secant is natural log of secant plus tangent, right? I mean, they sort of go together. But anyway, since the derivative of tangent is secant squared, the integral of secant squared is tangent, right? So these three you should have memorized. The rest of them, maybe not so much, right? Tangent squared is, the integral of tangent squared is tangent minus x, okay? And then you've got tangent cubed, secant cubed, and then you've got these general formulas, just like you had for sine and cosine, okay? So these could come in handy at any moment, so they're nice to have on hand. But again, the question is, well, what do you do if you've got both? What if you've got like a tangent to the m times a secant to the n? And once again, your book has a really nice table for how to deal with this scenario. This is on page 427 of your textbook. Let's take a look. Let me, 427, here. Okay, and you'll see that it's like a very similar set of procedures, okay? But it's not exactly the same. So here's what you do. If n is even, so if the power on secant is even, whether m is even or odd, it doesn't matter, right? As long as n is even, what you're going to do is split off a factor of secant squared. So not just secant, but secant squared. So obviously, if it's a secant squared, you're already done. If it's a secant to the fourth, then you're going to factor it as secant squared times secant squared. If it's a secant to the 12th, you're going to factor it as secant to the 10th times secant squared, right? You want to split off a factor of secant squared. And the reason you want to do that is because then the rest of your secants can be rewritten as tangents using this Pythagorean identity, okay? And so everything else you'll be able to rewrite in terms of tangent, and so then you can let u be tangent x, and the derivative of tangent x is secant squared, and that's why you needed to peel off a secant squared so that you could make your u substitution, okay? So that's what you do if n is even, if the power on secant is even. If the power on tangent is odd, whether the power on secant is even or odd, it doesn't matter. If the power on tangent is odd, then you're going to split off a factor of secant tangent. So you're going to take one of the secants, steal it from here, take one of the tangents, steal it from there. And the reason you're going to do that now is because when you can rewrite everything in terms of secant, make the u substitution, u equals secant x, and then the derivative of that is secant tangent, which is what you split off here, right? So that's what you do when m is odd. So then the only question is, what if m is even and n is odd, right? So if m is even and n is odd, well, then you just have to use relevant identities to reduce the integrand to powers of secant alone. And you do that using, again, Pythagorean identities. Okay. So let me walk you through some examples of that situation. Okay, so let's evaluate. Let's do the integral of tangent squared x secant to the fourth x dx. Okay, so this is a scenario where they're both even. So in particular, n is even, right? And so what do? We split off a factor of secant squared and then make the u substitution u equals tangent x. Here's our relevant Pythagorean identity, right? Secant squared is tangent squared plus 1. So we're going to split off a factor of secant squared, rewrite the rest of our secants in terms of tangent if we have any others. Oh, we will. And then make this substitution. Okay? All right. So this is going to be tangent squared, secant squared, tangent squared x, secant squared x, secant squared x. Secant squared x we can rewrite as tangent squared plus 1, right? Tangent squared plus 1. So and this other secant we want to leave like this so that we have the derivative of tangent sitting right there for our u substitution. So, so let u be tangent x, then du is secant squared x dx. Right? It's beautiful, right? And so you're going to have u squared times u squared plus 1 du. Or in other words, u to the fourth plus u squared du. And the rest is history, right? I haven't finished any yet, so maybe I'll finish this one. U to the fifth over 5 plus u cubed over 3 plus c. And u was tangent x. So this is tangent to the fifth x over 5 plus tangent cubed x over 3 plus c. And there they are, right? There it is. That's all there is to that. Let's look at another one. Let's do tangent cubed x, secant cubed x dx. Okay, tangent cubed, secant cubed. So this is going to be a situation where n is odd. So the exponent on our tangent function is odd. And so for that one, we're going to want to split off a factor of secant tangent, rewrite all the rest of our tangents in terms of secant, right, which we can do using this Pythagorean identity, and then let u be secant x because du is going to be secant tangent, right? Okay. So this is going to be tangent squared x, keep forgetting, secant squared x, and then secant x tangent x dx. And then tangent squared we can rewrite as secant squared minus 1, right? So this is going to be secant squared x minus 1 times secant squared x times secant x tangent x dx, right? That thing's going to be our du, right? Because now we can let u be secant squared x. Not secant squared, sorry, just secant x. Let u be secant x. Then du is secant x tangent x dx. Right, there it is. And so we get integral of u squared minus 1 times u squared du. That's just u to the fourth minus u squared du. And the rest is history. Okay. All right. So very nice. One more. Let's do integral of tangent squared x secant x dx. Okay, so this is a scenario where n is even and n is odd. So it puts us right down here. So all we can do with these is use relevant identities to reduce the integrand to powers of secant alone. So we just want to get everything in terms of secant. And the reason we can do that is because m is even, right? So we can use a Pythagorean identity to reduce tangent to secant. Okay, so let's do it. So tangent squared is secant squared minus 1. And that's going to give us secant cubed x minus secant x dx. You can split that integral. I'm going to run out of space unless I make the next line bigger. So I'm going to say this is secant cubed x dx minus secant x dx. Okay. Now, secant cubed was one of those formulas, right? Formula 26 from the textbook. So you can copy that down. And secant x you should have memorized, right? It's natural log of secant x plus tangent x. So just copying the formula down now for secant cubed, I've got 1/2 secant x tangent x plus 1/2 times natural log of secant x plus tangent x. Okay, that's all just this first part. And then this part is minus natural log of secant x plus tangent x. And now, this is kind of nice because we can combine some like terms here, right? Since these terms match, right? It's 1/2 minus 1 would be negative 1/2. So this is just 1/2 secant x tangent x minus 1/2 times the natural log of secant x plus tangent x plus c. And that's that one. Okay, now, so we've talked about sines, cosines, tangents, and secants. You may wonder, like, well, what if you've got like a sine and a tangent, or like a secant and a sine or something? Well, for those, you can always use identities, right? Like if you've got a sine and a secant, rewrite the secant as 1 over cosine. So then if you've got a sine over cosine, you can usually do some kind of u substitution. Derivative of sines cosines, so it's like sitting up there, right? Or if you've got tangent times cosine, well, tangent is just sine over cosine, so the cosines will cancel and you'll just end up with a sine. If you've got cotangents and cosecants, then you're going to do the same kind of thing that we've done with tangents and secants. So there's really nothing new there. And so that's really all we have to say about these things. So that's that. I'll leave you there.